In this video, we will be discussing the four fundamental gas laws: Charles' law, Boyle's law, Avogadro's law, and Gay-Lussac's law. Now, each one of the four fundamental laws is essentially looking at two of our primary variables when we're dealing with gases. The four primary variables are pressure, volume, amount of substance, typically measured in moles, and temperature. So Boyle's law is looking at the relationship between pressure and volume, while keeping the amount of gas in the form of number of moles constant and the temperature constant. Charles' law looks at volume versus temperature, keeping pressure and amount of substance in the form of moles constant. Avogadro's law looks at the relationship between volume and the amount of substance that you're working with, where the amount of substance is measured in moles. And Gay-Lussac's law, which is looking at the relationship between pressure and temperature, again keeping your other two variables, volume and number of moles, constant. The first law that we're going to look at is Boyle's law, which was developed by Robert Boyle and Robert Hooke in the late 1600s. The experiments that they did involved using a J tube, which is essentially a glass tube which has a capped end where the low end of the J is at, and the high end of the J, the right side in this case of the J, is open, and they would pour mercury into that end. So Robert Boyle, Robert Hooke, using a J tube, measured the volume at the small end that the gas sample took up while applying different pressures. The way that they applied the different pressures was by adding mercury into the long end, the right-hand side of the J. And because mercury is very massive, that was a good way of being able to add pressure. And because it's a liquid, it prevents the gas from escaping. Now, what they observed was that there was an inverse relationship between the volume that the gas occupied in the small end of the J and the pressure, or the amount of mercury that they were pouring in. What this means is that as one increases, the other one decreases. So as you increase the pressure, you decrease the volume. If you increase the volume, you decrease the pressure. Another convenient way of carrying out this experiment would be using a piston system. What a piston is essentially it's a closed container that has one end or one wall of the container that is movable. A common place that you'd find these is in like automobile engines. The piston is where the combustion occurs and how we get energy out of that particular system. So in a piston, we could have, let's say, a certain quantity of gas that occupies 1 liter at 1 atmosphere of pressure. When we apply a kilogram of weight onto the top of the movable wall or the piston. If we remove the kilogram weight and then apply a 2 kilogram weight, so essentially we're doubling the pressure, or we're doubling the amount of weight that's being exerted, or the force that's being exerted onto the top of the piston, what we find is by doubling the mass, we double the pressure, the volume gets cut in half, right? So if we double the pressure, we half the volume. If we go in reverse, if we double the volume, we have to half the pressure. So the relationship between volume and pressure looks like this as a curve. If we look at a slightly different way of graphing our data, so if we look at having maybe the inverse volume on the x-axis, so if we put 1 over volume on the x and pressure on the y, what we find is that there's a linear relationship between the two. It has a zero intercept, which means that our equation for this would be our pressure is equal to some constant times 1 over volume. We can rearrange this expression, moving the volume to the other side, and we end up with our pressure times volume is equal to some constant. And this part here, this relationship of pressure times volume for a particular gas sample is being equal to a constant as long as you don't change the temperature, is at the heart of Boyle's law. So a real-world example of Boyle's law is scuba diving, right? So if you ever go scuba diving, you'll find that for every 10 meters of depth you go down, the amount of pressure being exerted onto your body increases by roughly 1 atmosphere of pressure. So if you're on the surface, you would feel 1 atmosphere of pressure from the air. But if you dive down to a depth of 20 meters, you have an additional 2 atmospheres of pressure, making a total of 3 atmospheres of pressure. Now, the way that scuba divers are able to breathe in and out at the deep depths of like 20 meters is you have a gas cylinder on your back that's at a very high pressure, and then you have a pressure regulator that you're breathing in through. The pressure regulator senses the pressure of the water surrounding you, and then adjusts the pressure of the air that it's sending into your lungs to counteract that pressure. That enables you to use your standard lung muscles to be able to inhale and exhale against that 3 atmosphere pressure. So the air that you're breathing in down at 20 meters is actually at 3 atmospheres of pressure. Now, where this can cause problems is if you're doing a dive and you're down at 20 meters and something goes wrong and you need to quickly surface. Let's say you have a full lung of air that you took down at 20 meters. Surfacing, because you are cutting the pressure by 1/3, that means the volume would triple. So if you had a lung full of air down at 3 atmospheres of pressure, when you hit the surface, you'll have 3 times your lung capacity. What that will do is it will cause your lungs to rupture. So one of the things you learn when you first start to scuba dive is if you ever have to make an emergency ascent, go up quickly, is that you should continuously exhale as you're going up. And if you go for certification, one of the things that you will be doing is you do a dive in a fairly deep swimming pool, you inhale, and then they have you ascend, and you'll be surprised at just how much air you're able to exhale. It's quite a bit. Now, this process of the lungs rupturing from an emergency ascent is different from the bends, which is a process in which the gas that's dissolved in your blood creates bubbles in your veins. This is an effect of Henry's law that we will actually be talking about in the next set of videos, but is not really part of our gas discussion. So let's look at a couple problems that are involving Boyle's law. And the way that we're going to handle these is going to be a very similar fashion to how you would handle Charles' law, Avogadro's law, and the Gay-Lussac's law once you have the basic relationship for how each one of those individual laws works. So let's say you have a sample of gas that is contained in a 1.25 liter container at 3.25 bar. If the gas is allowed to expand until the pressure reaches 1.01 bar, what will the volume of the gas be? So one of the first things that you're going to want to do for these problems is draw a picture so that you can better understand what's going on. So we have our container, and because we're working with pressures and volumes, it's very convenient to use that piston model. So we have our container, we have our movable wall in the middle, and we're starting with an initial volume. Our volume at location 1 is equal to 1.25 liters. The pressure that corresponds with that, the pressure at location 1, is 3.25 bar. Now what we're going to do is let it expand until the pressure reaches 1.01. Because the pressure is going down and we know that there's an inverse relationship from Boyle's law between pressure and volume, if the pressure goes down, the volume has to go up. What this tells us is that the piston is going to move up, meaning that our volume after that pressure decreases is going to be larger. So our pressure at point 2 is going to be 1.01 bar, and our volume at location 2 is, well, that's what we're trying to find. But what we know is that volume 2 will be greater than volume 1 because the pressure decreased, so the volume should increase. Now, from our relationship that we had talked about, where if we're looking at a plot of 1 over volume versus pressure, it gives us a straight line with the intercept being at the origin at 0 for 1 over volume is equal to 0 for pressure. What this tells us is that, again, our pressure is equal to some constant times 1 over volume. We can rearrange this moving volume to the other side, getting the essence of Boyle's law, which is pressure times volume is equal to some constant. Now, if we are maintaining the gas inside, not adding or removing from it, and maintaining the temperature, so we're keeping the number of moles constant and the temperature constant, the constant stays the same as we adjust the pressure and the volume. What this tells us is that the pressure at point 1 and the volume at point 1 is equal to a constant, and because we're not changing the temperature or the number of moles, that constant is equal to the pressure at point 2 times the volume at point 2. What we can do is use this relationship, P1V1 is equal to P2V2, to find V2. So we're interested in V2, we're going to divide both sides by P2, giving us an expression of V2 is equal to P1V1 over P2. So that is going to be, using our values, P1 is 3.25 bar times V1, which is 1.25 liters. This is divided by P2, which is 1.01 bar. Our bar are going to cancel out, giving us the only unit that's left, which is liters, which is good because we're trying to find a volume. So our end answer should be in liters. If you plug this into your calculator, you'll find that V2 is equal to 4.0223 liters. Now, each one of our values in our calculation had 3 significant figures, so our end answer should have 3 significant figures. So the answer that we would use would be 4.02 liters. So that would be our end answer for this problem. Looking at another problem, let's say you have a sample of gas in a 2.5 liter container at 3.65 bar. If the gas is compressed to a volume of 1.00 liters, what will the pressure be? So again, to understand what we're working with, let's draw our piston setup. We have our piston. We have our initial volume. Our volume at location 1 is 2.50 liters. Our pressure at position 1 is 3.65 bar. Now, we are decreasing the volume, which means the piston is moving down to some lower location. Our volume at point 2 is 1.00 liters. Our pressure at point 2 is, well, that's what we're trying to find. But we can tell, because we know that there's an inverse relationship between volume and pressure, because we are decreasing the volume, we should be increasing the pressure. So using our basic Boyle law relationship of pressure times volume is equal to a constant, and because we're keeping the number of moles and the temperature constant, P1V1 is equal to a constant. That same constant is equal to P2V2. We're trying to find P2, so we're going to divide both sides by V2, giving us P2 is equal to P1V1 over V2, which is equal to, putting in our pressures, that would be 3.65 bar, times V1, 2.50 liters, divided by V2, which is 1.00 liters. If you plug that into your calculator, you will get 9.125 bar. Our liters cancel out, and so we should have units of bar. Each one of these has 3 significant figures, and so our end answer, P2, would be 9.13 bar. That would be our end answer for this problem. Now, the next one that we're going to look at is Charles' law. So in Charles' law, we are looking at the relationship between temperature and volume. So Jacques Charles, however you properly pronounce it, formulated the what we now know as Charles' law in the 1780s by looking at the relationship between volume and temperature. So essentially taking a closed container with a movable wall, sort of like a piston, heating up the gas inside and recording the changes in volume. So what he found was that the volume and the temperature of gases are directly proportional to each other. As you increase the temperature, you increase the volume. As you decrease the temperature, you decrease the volume. So if we plot temperature on the x-axis and volume on the y-axis for a variety of different containers, so in each one of these we have a different number of moles, we're maintaining the same pressure, and for each one of these lines we're maintaining the same number of moles. It's just that each one of these lines is in a different container with a different number of moles. So you're essentially allowing the piston to move against atmospheric pressure, and what Charles, or Jacques Charles, would have been doing would be using different masses of gases in each sample. So if you look at the relationship of how temperature and volume change with each other, and you plot it as you cool the gas down, so decreasing the temperature and measuring the volume, what you'll find is that the intercept, where the volume is equal to 0, is the same for each one of the containers. So the temperature at which you should have a 0 volume is the same regardless of how many number of moles you have. Right? So long as you're keeping the pressure the same, they're all going to end up giving you a linear relationship that hits the x-axis at the exact same location, and that corresponds to a temperature in Celsius of negative 273.15 degrees Celsius. That temperature is what we refer to as 0 Kelvin. That is absolute zero. It's the lowest temperature you can get to. Essentially what we're saying in terms of the kinetic molecular theory is that the atoms are no longer moving around in space. They're not occupying any additional volume. So if their volume is 0, their temperature, you've essentially pulled all the kinetic energy out of them. They're not moving at all. So this is the smallest volume, which corresponds to the lowest temperature that you can possibly have. Right? So that's how you actually derive the value for absolute zero. Is you do something like Charles' law, where you graph volume versus temperature, and you extrapolate it back down to a 0 Kelvin, or negative 273.15 Celsius. Now the reason you can't actually graph it all the way back down to 0 is for any gas sample that you're using, at some point the gas is going to condense into a liquid, and then that liquid is going to freeze into a solid before you hit absolute zero. So Avogadro's law is similar. This time you're looking at volume compared to number of moles. So what Avogadro did was he took greater and greater amounts of a particular gas sample and looked to see what the volume was at a given pressure and temperature value. What he found was that if you increase the number of moles, of an object or a number of moles of a gas, the volume increases, and they're directly proportional to each other. So if you double the number of moles, you end up doubling the volume that they occupy. And equal volumes of gas contain the same number of molecules no matter what the gas is. So if we have 20 liters of gas, no matter what the gas is, as long as we're working at the same temperature and external pressure, it will have the exact same number of moles. The last one that we're going to look at is Gay-Lussac's law, which is the relationship between pressure and temperature. Now, the graph of Gay-Lussac looks fairly similar to Charles' law. The difference being we're looking at pressure instead of volume. That's pretty much the only difference. For the Gay-Lussac, what we can actually do is, again, plot pressure versus temperature at a variety of closed sealed containers. And what we'll find is that as the temperature decreases, the pressure will decrease. We can then extrapolate the values back down to a zero pressure value, and what we'll find is that it intercepts the x-axis, the location where the pressure is equal to 0, at negative 273.15 degrees Celsius, or 0 Kelvin. This again is where the definition of 0 Kelvin came from, is once you come down to a particular temperature, there is no longer any external, or there's no pressure being exerted onto the side of the container, which means you've removed all of the kinetic energy from the molecule, and there's none left to remove, and so you can't reduce the temperature further. So, a little bit of a summary. Boyle's law is pressure versus volume. Pressure and volume are inversely related. So if we take pressure times volume, that's equal to some constant. So this means that as pressure goes up, to maintain the constant, the volume has to go down. Charles' law. Charles found that the volume and temperature were directly proportional to each other. So as one goes up, the other one goes up to maintain the constant. Avogadro's law is looking at volume versus number of moles. They are directly proportional. So as volume goes up, number of moles goes up. Gay-Lussac looks at pressure versus temperature. As pressure goes up, temperature goes up to maintain the constant. So what we'll find in the next video is how each one of them, how we can incorporate all four of these laws into one unifying law, and we will call that the ideal gas law. What we'll be able to do with that is, given three of the values, pressure, volume, number of moles, and temperature, so given three, we'll be able to determine what the fourth should be.